Hello everyone. In today's episode, we continue our discussion on the electric field shielding of current probes. Okay, so in our last episode, we demonstrate the concept of E-field shielding, and that's why if you look at a commercially made current RF current probes, they all have this casing with little slots inside to shield the electric field. So in today's demonstration, we started with a very simple one. Okay, so as you can see, this is a 30 amps rated Hall effect based current probe. Okay, and it can measure a current up to 30 amps maximum. Okay, and I use this a lot for sort of harmonics analysis and things like that, right? But I just wanted to demonstrate you that probes such as this, right, they are designed for low frequency measurement. Okay, therefore they don't actually focus on the E-field shielding. So that's why showing here, which is connected to our channel 4, is this current probe. Okay, as you can see, I didn't even switch it on then. This is off. Okay, it's already picking up noise. And where does this noise come from? Well, let's first disable our output of the generator. Okay, so making sure there is no noise, let's say, or signal coming from the generator side, yet this still picks up noise in ambient. So this noise could be the switchable power supply nearby or equipment nearby, but as you can see, they do pick up noise. So be careful when you're using this kind of probe, right? So they do the job, especially you're measuring this close to this rated current, right? So 20 amps, 30 amps, things like that. This is really, really good. And when you're using this current probe to measure signals to that scale, these kind of tiny little noise current probably doesn't really matter. However, if you ever want to use this to measure noise or small signals within this frequency band, then it could be a problem. Okay, so as you can see here, as I mentioned, even this is off, you still pick up noise, and then now I just switch it on, you see it's the same thing. That RF noise cannot be filtered out by this probe, which makes sense because this probe only is designed for bandwidth up to 100 kilohertz. So as long as it does its job, it's good. Okay, so that's just a quick demonstration of your Hall effect sensor based current probe. Okay, in our previous episodes, right, we demonstrate the concept of using this small near field probe connected to the signal generator, right, and we supply again the same voltage, right, in this case voltage, square wave 5 volts peak to peak applied to this near field probe, and we use this type of current probe, right, to measure the current along the conductor, right. So we showed in our previous discussion, right, that you see there's an overshoot and ringing during the measurement, and we asked the question, is it real, like the current really is like with overshoot and ringing, or this is due to measurement error, right? So one thing I can do is I can sort of move this current probe, right, and you can see the ringing and overshoot start to change, right, as I move alongside this conductor. So you can see as I move the current probe, the overshoot and ringing behaves differently, right? So it does give me the feeling that perhaps it is due to the measurement rather than the waveform itself. So how do we prove this then? Now, one idea is that if you look at this near field probe, we mentioned this is a unshielded near field probe, okay, in the sense that this is just a wire, bare wire, right, with the heat shrink, and that's it, right? There's no shielding capability of this near field probe. Whereas if we look at this kind of, again, it's a homemade probe, near field probe, but the difference between this one and this one is that this actually has some E-field shielding because we use the coaxial cable, right? And I just soldered in this manner, and of course it would not work because it's basically is like a Faraday cage. So what you do is you cut a small slot in the center here. So that would allow the current magnetic field pickup, right? Because the magnetic field will be picked up by the inner conductor of this coaxial cable, whereas the outer shield, this side and this side, forms a good E field shielding, right? Particularly at this center point, because the E field induced voltage will be cancelled out. So that's how this E field shielded near field loop works. Okay, so now let's have a look. If I connected this shielded loop to this generator, okay, and I'm using the same probe to measure it, let's see the difference. Okay, so you can see that again there are some small overshoot and ringing there, right? But if I move it to where the maximum E field cancellation is, right, it's here. That's where the slot sits. The overshoot and ringing is a lot less compared with the unshielded loop. Okay, so this does suggest that the overshoot and ringing we measured previously is due to capacitive E field loading rather than the true signal going through the conductor. Okay.